Okay, focusing on linear regression or building that model or building our line of best fit, there's a lot of important vocab here. Remember that when we're talking about the model, what we're doing is talking about that line of best fit. Again, this is just a model, it's just an estimate of what's happening. Our predicted values, we usually call this y hat. This is the estimate that your model creates. Okay, residual is a common word. Residual is the difference between the observed value and its predicted value. So residual, I always think of as your actual minus your predicted. Line of best fit is sometimes called the least squares residual, the least squared residual line. Sometimes it's called that, but that is basically just your line of best fit or your linear regression. Slope and y-intercept we've talked about quite a bit. Remember that slope is telling you how rapidly your y value changes with respect to x, and your y-intercept tells you where that line crosses the y-axis. I would find some space on here to write down the interpretations of slope and y-intercept, so I'm just going to add this on kind of off to the side here. Okay, when I am interpreting my slope, we want to make sure we're showing the grader we understand that the slope is just from a model. So we like to say that the model predicts. So I'm going to say the model predicts that for every additional x, this is where you would input your x variable, we expect the y variable to either increase or decrease depending on the sign of the slope. If your slope is positive, it's increasing. If it's negative, it's decreasing. By an average, slopes are always averages, so we want to make sure we have that average there of blank, and this is where you input your slope. Okay, y-intercepts are slightly easier. Y-intercept is telling you where this line crosses the y-axis. That means that your x variable is always 0. So again, we are going to start with the model predicts. That when your x is 0, we expect the blank, put in your y variable, to be blank, where you put your y-intercept. Okay, those are two more formulas or templates, however you want to think about it, that you definitely want to have memorized for that AP test. Okay, with our slope and y-intercept, I also recommend that you can find it on computer output. So I'm going to jump ahead in my packet to page 12 and look at that computer output here. With your computer output, they're always going to start with listing, predictors, or sometimes they just say variables here. Next to the constant is always your y-intercept. There will be a variable underneath it. That variable is your x variable, and then the number right next to that is your slope. So make sure you're able to read that computer output. Remember, we do need the standard error, standard deviation of slope for linear regression inference. So that's when we're finding those when we're finding confidence intervals in hypothesis testing. This P does stand for your p-value, so we would need that for our hypothesis test. But the big things when we're working with just linear regression, finding the line of best fit, all that stuff, should come from this first column under coefficient. Okay, some important equations here. Kind of already talked about this a bit, but your residual is your observed or your actual minus your predicted. You could think about this as your actual y value minus the predicted y, so there's that little hat on top. And these are just different variations of that same formula. This right here is the line of best fit. Remember that B1 is representing your slope, so the second formula here is for slope. This B0 is your y-intercept. We did look at some multiple choice questions this unit where you need to know these formulas here. These formulas are given to you, so the slope and y-intercept formula will be given to you on the AP exam, which is nice, but you do need to know which one represents slope, which one represents y-intercept. You would only have to use these formulas if instead of giving you data, they were telling you the mean and the standard deviation for each of those variables. So instead of saying, here's all my data, they're going to say the standard deviation of y and the standard deviation of x are these two here. Just some random things to know here. A negative residual means that the predicted value was too big, so we had an overestimate. I drew a quick little scatter plot here, randomly drawn my line of best fit. And then this point here would have a negative residual. Our line of best fit was higher than the actual value, so that's our overestimate. Positive residual will go the opposite way, so that would be a dot that's above the line of best fit, positive residual. But what happened was our line was too low, it made an underestimate. Keep in mind that R cannot be greater than 1. Oftentimes you'll see kind of random multiple choice questions where they say, I found a correlation coefficient of 1.79. It shows that it's a very strong relationship. That is absolutely false because that R cannot be greater than 1. Sometimes you'll be asked to look at a residual plot and draw conclusions based on that residual plot. Remember, if there is no pattern in the residual plot, then a linear model is appropriate. So when you make a residual plot, we want to see randomness. For example, let's say this is my residual. I want to see just kind of random dots all over, evenly spread, evenly scattered. If there's a pattern in your residual plot, that's telling us a linear model is not appropriate. So for example, I might see something that looks like this. It's very clearly a pattern, it looks like a quadratic. That would tell me that a linear model is not appropriate. Okay, R-squared values. That's another one of those templates that we should be memorizing. R-squared measures how close the data is to the regression line. It's always between 0 and 100%. The larger R value means there's less scatter, so the model is a good fit. So we are wanting large R-squared values, means that our model is doing a very good job of making predictions. Okay, a few more things about this linear regression or building that model. You want to be cautious when you're looking at extrapolation. So what extrapolation does is it predicts y values for x values that are very far from the ones that were used to find the model. For example, I could be given data that's, let's say, starting here at 0, going to 10. Here is my scatter plot. Okay, and then they might ask me to make a prediction for when x is 20. Well, x is 20 is like way over here. That's far beyond my data set. I do not want to be making a prediction that far from my data, so that would be extrapolation. I remember that outliers are any points that stand far away from the others or you think are unusual. Points that have high leverage are points whose x values are far from the mean of x. For example, if I drew a little scatter plot here, I'm just going to make it go positive. If I wanted a point with high leverage, I would have to put it far away. It's an x value far from that average. My guess is that the average x is somewhere in the middle there. This point has high leverage because the location of this point can severely impact my model. If I move my points way up here, now it's going to make my slope very positive. versus if I moved that point down here, it's going to draw my slope a little bit more negative. Okay, this point here also can be considered an influential point if omitting this point from the data results in a very different regression model. So if I were to take away these points, then my slope would be, relatively straight, so that would be influential. Remember to watch out for lurking variables. These are variables that are not explicitly part of the model, but affect the way that the variables in the model appear to be related. So when we looked at these lurking variables, we looked at the number of ice cream sales and the number of murders. And it had a positive relationship. So we said, does that mean that the more ice cream we sell, the more murders there are going to be? No, we said that a possible lurking variable here would have been temperature. As that temperature increases, more people are buying ice cream, and statistically, as the temperature increases, more murders are occurring. Okay, just a few other important points here. I'm just going to point out, what I think is the most important. It's the second to last bullet point. A strong correlation still doesn't indicate a cause and effect relationship because of these lurking variables. The only way to prove causation is through an experiment. So please, please, please do not say that ice cream sales are causing murders. There's no way to prove this causation unless we run an experiment.